Hello, guys. My name's Harry, and I'm from the class of 2017. Today I'm going to be solving free response question number 2 on the rotational mechanics review packet. Now, the problem reads, a solid sphere of mass 1.5 kilograms and radius 15 centimeters rolls without slipping down a 35-degree incline that's 7 meters long. Assume it started from rest. The moment of inertia of a sphere is given by I is equal to 2/5 mr squared. Part A says calculate the linear speed of the sphere when it reaches the bottom of the incline. Okay, so we know they want us to solve for the velocity at point B. They do. They want us to solve for the velocity at point B. Now, it's evident that this problem is a conservation of energy problem, but it's got a few twists, and I just wanted to refresh your memories of some equations that I'm sure you've seen before. Over on the side, we can see that the kinetic energy translational is equal to 1/2 mv squared, that kinetic energy rotational is equal to 1/2 times the moment of inertia times omega squared. And then we can also see that tangential velocity is equal to omega r in cases when objects aren't slipping. And obviously the difference between translational and rotational kinetic energy is translational kinetic energy is the energy of an object due to its motion, while rotational kinetic energy is the energy that an object requires to rotate. Now let's delve straight into this problem. As you can see, I've started off with the signature UA is equal to UB, which signifies this is a conservation of energy problem. I've rewritten this as the gravitational potential energy of A is equal to kinetic energy B plus the kinetic energy rotational. And this is a key point. We have to recognize that at point A, the object has gravitational potential energy, but then at point B, it has both translational kinetic energy and rotational kinetic energy. It's got to have both. This is key. So we rewrite this in equation form as mgh is equal to 1/2 mv squared plus 1/2 I omega squared. And I write that same thing again, except that I stopped because I want to make two key substitutions into the equation. We need to see that I is equal to 2/5 mr squared for that of a sphere. That was given to us. And because the object isn't slipping, it says so in the problem, omega squared is equal to v squared over r squared. And that can be found by solving for omega with this equation. We find that it's tangential velocity over the radius. Now, you math lovers like me can rejoice because the radiuses, they cancel out, r squareds cancel out, and guess what? The m's do too. Our equation is now so much easier. GH is equal to 1/2 v squared plus 2/10 v squared. This v squared is the same. It's the linear speed at b. When we combine like terms, we get GH is equal to 7/10 times the velocity of b squared. Solving for the velocity of b, we see that it equals 10 GH over 7 square root. Plugging in the numbers, we get 10. Now, I hope you guys know that gravity is 9.8 meters per second for the acceleration. And we found height by using some trig up in the corner, which I've already solved. We can see that because they give us the 35-degree angle, we can clearly solve for the height. And the height comes to be 4.015. Running this big thing through my calculator, I get 7.5 meters per second. And this is the key idea. This is the linear speed. Unfortunately, though, guys, we got two more parts. So part B reads, determine the angular speed of a of the sphere at the bottom of the incline. So we solved for linear speed v, but they want omega. How are we going to solve for this? Well, we know that tangential speed is equal to I almost said w there. I meant omega. And omega is equal to v over r, which we just solved for. 7.5 over 15 centimeters, or 0.15 meters, gets me an answer of 50 radians per second. That's huge. One way that helps us see the difference between rotational and translational kinetic energy is this cool little video that I found. It shows the rotational and translational kinetic energy. We can see that the rotational kinetic energy is when the ball is actually rotating, but translational is when it is the energy required to move it down the ramp. So I think that that's just a cool animation that helps us get an idea of that. Part C reads, does the linear speed depend on the radius or mass of the sphere? Does the angular speed depend on the radius or mass of the sphere? We can tackle this in two different ways, in two separate questions. Let's look at v. We know that the speed, that v is equal to this for linear speed. And that equation tells us that neither mass or radius is needed to determine or to depend on the mass or the radius of the sphere. In short, linear speed does not depend on velocity or radius, but omega does. Omega is equal to v over r. So yes, it depends on r, but no on the mass. Thanks for listening, guys, and have a good day.